Hey there, I'm Dominic Romero.
My name is Diane Pacheco.
My name is Jasmine Garcia.
I am Sanjay White, and together we are the Z Fighters. We'll be introducing our product today, the Farmhands. The agricultural sector faces significant challenges in pest control, with traditional methods often being labor-intensive, inefficient, and environmentally risky. Current practices rely heavily on manual labor and chemical spraying, leading to high operational costs, environmental degradation, and health concerns. The Farmhands project addresses the shortcomings of conventional pest control. Our target audience is going to be mainly farmers, agricultural companies, DIY enthusiasts, and even just your regular grocery shoppers, with our indirect customers being researchers, environmental organizations, construction infrastructure companies, emergency services, and security firms. We need these bots to monitor the crop health. We have to have a rechargeable ground station. We need to manage the waste and disposal system, apply insecticide or pesticide up to 50 acres per hour, fly an average height of 20 to 30 feet, record and store data about the fields, adjustable coverage area, remotely operated, and autonomous navigation. Next, we'll touch on our individual robots. The Roost will be introduced by Dominic, Cyphernova will be introduced by Jason, Harvest Eye will be introduced by Diane, and the AgriGuard will be introduced by myself.
Hey there, my name is Dominic Romero and I am showcasing the Roost, our team's charging and docking station for our agricultural aiding aerial swarm. Following a day's work of monitoring crop health, applying fertilizers, repellents, and sowing the area of operation, the drones make their return, hovering smoothly back to the station, guided by a sophisticated GPS system and algorithms. As they make their descent onto the landing pads, the drones are recognized by the distance sensors, which triggers the activation of the wireless charging system. Their batteries are then quickly replenished by the energy stored inside the onboard lithium battery bank via the use of eco-friendly solar panels that harness solar energy with minimal environmental impact. For my circuit designs, we have the raising and lowering circuit for the telescoping landing pads. In operation, when a user presses the raise or lower push buttons, the Arduino microcontroller receives this input and activates the corresponding relay to drive the motor in the desired direction, whether that be up or down. For the wireless charging circuit, we have an Arduino microprocessor that will process the input from the distance sensor, which detects the presence and altitude of the drones as they approach the landing pads. Once the sensor detects the drone's altitude to be within 12 inches of the landing pad, the inductive charging coils are then activated. The following flowchart shows the telescoping landing pad. When landing pads recess below the roof, a shutter automatically deploys above them, creating a watertight compartment for drone storage during transit or inclement weather. In the recessed position, the system actively awaits a call signal from the raised landing pad push button. Pressing the push button opens the shutters and begins elevating the landing pad using the forward-reverse motors. This allows the drones to take flight securely without obstacles. The wireless charging flowchart illustrates the processes for detecting the drone using ultrasonic distance sensors, starting the charging mode, monitoring progress, and completing the charging operation safely. The telescoping landing pad circuit uses an Arduino microcontroller, two push button switches on holding circuits to raise and lower the platforms, and the forward reverse motor. This circuit operates much like an elevator circuit. Lastly, the wireless charging circuit features an Arduino microcontroller, function generator and oscilloscope to control line voltage, LCD display, and an ultrasonic distance sensor. Chargers are activated as drones descend within 12 inches of the landing pad surface.
Hello everybody, my name is Jasmine Garcia. Thank you for joining me as I introduce Cyphernova, the pioneering agriculture drone reshaping farming also known as the sprayer bot. Here's the glimpse of its capabilities. It will efficiently strategize spraying, factoring in command, and pest detection. It calculates pesticide amounts based on the infestation and treatment area size. The spraying mechanism adjusts for optimal patterns and intensity. It navigates predetermined routes while consistently treating areas. Plus, it utilizes obstacle sensors for seamless navigation. Additional key features includes all-weather durability, including wind ranging from 15 to 35 miles per hour, and extreme temperature ranging from negative 20 degrees to 110 degrees Fahrenheit. Modular components extend their lifespan up to 3 to 4 years, and adaptability. Additionally, it includes 4 high-efficiency propellers for stable flight control, a top-tier UHD camera for precise aerial imaging, a versatile reservoir for various payloads like insecticides, pesticides, herbicides, or fertilizers, 4 sprayers for uniform pesticides distributions, LED lights for battery indication, and low light visibility. Moreover, it has rechargeable batteries that offers extended flight times for uninterrupted operation. Binocular vision and distance sensors enable the drone to navigate and avoid obstacles with enhanced accuracy. This drone flies at 20 to 30 feet, offers 8 to 12 hours of flight time, built with durable carbon fiber and aluminum alloy, and it can travel at a speed range of 0.5 to 1 meter per second. This drone's key electrical components includes 4 DC motors for stable flight, 2 9-voltage batteries for sustained powers, 4 servo motors for precise spraying and maneuvering, and 2 distance sensors for navigation and obstacle avoidance, and LED lights for power status indication. Let's dive into the structure of this Arduino code. We have defined the variables and the pin numbers for distance sensors, motors, motor control, and pump pin. In a setup function, we initialize the serial communication, the sensor pins, the servo motors, and the pump pin along with the LED lights. The loop function section is where our drone reads distances from the sensors, move based on the readings, activates the sprayer pump if needed, when needed. We have defined the functions for reading the distance, stopping the drone, moving forward, ascending, and activating the sprayer pump. This flowchart illustrates the Arduino code for the drone step by step during the operation. It will receive a command from the central hub. If no, then it enters a loop. If yes, then the drone will take off. It will start reading the distances through the ultrasonic to detect obstacles. It will initiate an emergency stop on obstacle detection. It will ascend and descend and moves forward when the path is clear, and it will activate the sprayer pump for treatment when needed. I will now demonstrate the simulation through Tinkercad. Here we are in Tinkercad. You can see my electrical component, and next to it is the Arduino code. I will start the simulation for you to see how it works. As you can see, the servo motor and the DC motor start rotating. The sensors are starting to read the distance. As you can see, the LED light just turned on. That means that the drone has full battery. That is it. Thank you for watching.
Hello everyone, my name is Diane Pacheco and I am in charge of Harvest Eye. It is the crop health monitoring bot. It's an aerial bot that uses a thermal imager, a moisture sensor, and a pH sensor to monitor the crop health. It also takes soil samples for further evaluation. This is an overview of what it looks like. And then these are some of the mechanical designs. So as shown, it has 2 9-volt batteries. You can see the battery ports are outlined in pink. It has 4 DC motors. The DC motors are outlined in green. The soil sample storage bin, which is black. And then it has 4 servo motors. The servo motors are the little white boxes. It also has an Arduino and a breadboard. This is a further mechanical design continuation. So it shows the moisture sensor, the pH sensor, the 2 ultrasonic sensors, and the front side of the thermal imager, as well as the dimensions of the drone itself. These are just a different angle of the drone, so a side angle and a back side angle, just so you can see how low the soil storage sample bin sits and how low the thermal imager itself sits. This is a picture of the circuit that I've used. The circuit itself has 2 ultrasonic sensors, as I showed previously on the actual drone itself, 4 DC motors, 4 servo motors, 2 9-volt batteries, an Arduino, a breadboard, and then all the connections between the components. This is the flowchart for the Harvest I bot. When you start it, it'll go to see if there's a signal from the command hub. If there is, it'll read the ultrasonic sensors, and then it can either actuate the arms of the drone for a landing, or it can retract the arms and start the motors for takeoff. If there's no signal from the command hub, it'll just loop back until there is a signal from the command hub. This is the Arduino design code. This is the Harvest Eye's actual circuit. We will simulate it right now. So we're going to start. We will see these servo motors actuate, and this is how the Harvest Eye works.
Hi again, I'll be presenting on our AgriGuard. This is our waste and disposal management bot. This bot was born out of a vision for sustainable agriculture. This groundbreaking innovation integrates cutting-edge technology to revolutionize pest management in the agricultural sector. Its mission is to enhance crop health, maximize yields, and minimize environmental impacts. Now let's look at the AgriGuard's mechanical design. The AgriGuard embodies a lightweight yet resilient carbon fiber frame, ensuring durability and agility in agricultural environments. Configured as a quadcopter with 4 brushless motors, it delivers stability and precision flight control for seamless navigation across diverse terrains. Equipped with a sophisticated sensor array, including high-resolution cameras, infrared sensors, LiDAR technology, and thermal imaging capabilities, our bot provides real-time data on crop health and pest presence. It also includes a waste storage compartment for hygienic waste disposal and boasts a modular design for easy maintenance and customization, catering to the specific needs of each farmer. Now let's dive into the circuitry of the AgriGuard. Engineered for versatility and responsiveness, our circuitry ensures seamless operation and real-time data analysis. Using serial input, our robot receives commands to check a variety of sensors, including the IR proximity sensor, the temperature sensor, and ultrasonic distance sensors, which we use in place for the LiDAR and camera in this instance. These sensors provide critical information on crop health and environmental conditions. Actuators such as DC motors for propulsion and servo motors for sensor tilt adjustment enable precise control and maneuverability. Data transmissions occur via serial output, facilitating real-time analysis and decision-making. The power supply system accommodates various energy resources, ensuring reliable performance in agricultural settings. In addition to our robust circuitry, the AgriGuard's functionality is powered by meticulously crafted Arduino code. Designed for efficiency and effectiveness, our code orchestrates the seamless interaction between sensors, actuators, and data processing algorithms. By receiving inputs from sensors, the code executes precise actions such as motor control and data transmission, enabling real-time monitoring and decision-making. Through meticulous testing and optimization, our Arduino code ensures reliable and responsive operation of our AgriGuard in the field. Now, let's visualize the operation of our AgriGuard through a comprehensive flowchart based on our algorithm. From pest detection to waste management, this flowchart illustrates the step-by-step process our robot follows to safeguard crops and optimize agricultural outcomes with clear decision points and action. Our algorithm ensures efficient and effective pest management while minimizing environmental impact. Now let's showcase how this circuit would work. So as you can see, we developed the circuit in Tinkercad. We have incorporated 4 DC motors for the propellers. We have 2 servo motors, one for tilting, one for panning of the camera, and we have this ultrasonic distance sensor as replacement for a camera or LiDAR. We have all these connected into our Arduino system here, and we have our Arduino code. If we go ahead and simulate this, and let's open the serial monitor, you can see as this process, it goes through the entire line of code, and once the circuit is complete, it sends a serial output to say that the waste collection is complete.
This is the central hub flowchart. When you start, the command hub will send out a signal to the pesticide bot. That bot will take off and begin spraying crops. Once it has sprayed all the crops, there will be another signal sent out to the crop health bot and the waste management bot to do their scans. Once all scans have been completed, a signal will be sent out to decipher whether the bots need to recharge. If they do need to recharge, the command hub will send out a signal to the ground station to prepare for charging.
Let's start with the crucial aspect of budgeting. Our research estimates the market-ready unit cost to be approximately $10,000. The estimation is grounded in meticulous analysis of component cost, labor, and other pertinent factors, as you can see on the slide.
In today's advancing world, agricultural robots are leading a revolution in farming, from planting to pest management. Our tailored swarm handles repeated tasks, allowing farmers to focus on strategic management. This investment promises increased efficiency, higher yields, and industry sustainability. Working on this project has allowed us to develop essential skills like communication, collaboration, time management, problem solving, adaptability, leadership, and accountability. Having guided the engineering process from start to finish, I believe our team can streamline procedures and shorten delivery times. Establishing systems based on our collective experience will improve future project outcomes. Here are the references. Thank you for watching.